Hi, this is Dr. S.P. Harsa from Mechanical and Industrial Department, IIT Roorkee. I am going to deliver my lecture 22 on the course of the strength of material, and this course is developed under the National Program on Technological Enhanced Learning (NPTEL). Prior to start this lecture, I would like to discuss like the concept which we discussed in the previous lecture, that if we have a spring, then what kind of deformations are there and what exactly the types of springs are there, and if you are talking about like the load application on the springs irrespective of the radial load or the twisting moment, then how the deflection will take place. And once you know the deflection, you can probably get like the stiffness of that spring, spring as the force point deflection, or we can simply get the value of the shear stresses for that. So all that kind of like the discussion which we made in the previous lecture. So we found that the like the spring has its own unique properties, and it has lots of application where you see where the brakings are there, or the clutch operations are there, or even in the automobile like where the shock absorbers are there. So it is a perfect because we have like the three main types of springs which we discussed in the previous section. One was like the helical spring according to the helix angle, and generally we are using, and you will find that many of the application even in your like the pen where like you want to control the motion of that lead, then the spring is there. Or right from that part to measure, you see like if we have like any like aeroplane, when it is landing, it is just you see when it is landing the shock absorbing is there. So it through tire you see, and when the tire is connected to that internal inertial frame, then the springs are there, the leaf springs are there in our automatic vehicle. So there are you see like right from the small application to the bigger application, lots of uses are there of the spring. And if we want to design the spring, then first you see if it is under the action of radial load, then like we calculated that actually what exactly the deflection is. So you see like we found that actually deflection is nothing but it is a direct function of the mean diameter of the spring, or we can say it comes when like a reciprocal relation with the small diameter d cube d to the power 4, or we can say it is reciprocal relation with this number of coils, or direct relation with the applied torque. So all these blah blah things which we discussed in this previous lecture. And also once you have the deflection, we probably find it out the spring stiffness or the shear forces or angle of twist, whatever like that. And then you see we discussed that actually when you have a spring and when it is under the action of not the radial load, when it is the twisting moment is there, then what is the maximum bending stresses are. So you see like when the twisting moment is there, again it depends on that actually how much twisting moment is applied, and due to that actually what exactly the shape is there. And we found that this angle of twist like the one end is so close, it is coming so close to the another end, so we are saying that it is the wind up angle. And we also calculated the wind up angle for the spring part. So this part we discussed in the previous section, and we found that you see if you want to design the spring, then again you see you have to be very careful that actually what exactly the influencing parameters are there, through which you see we can simply say that yeah, this much deformation will come under the action of these radial load or under the action of these twisting moments are. So now you see again, and the last portion you see we just wanted to like focus that actually if the spring application, if more than one springs are there, means if we have the two springs and if they are connected in the two ways, then how you see like the stiffness will come. So again you see I just wanted to start from that portion, and that then you see we would like to go that actually when we have a beam or we have a member which is subjected by a flexural loading, then you see how we can define and what kind of loadings are there and what types of these structures are. So this you see kind of discussion which we are going to discuss in this lecture. So we are starting from the spring part, that if we have the spring, two springs are there, and if they are in the series form. So if these two springs are there and like with the different stiffness, because you see both springs are of the different material, so they have like the different stiffness altogether, and if they are joining just one by one at the two extreme ends, so you see these ends they are joined to each other and they are carrying the same load. So you see if we are keeping radial load at the downward direction, they are said to be connected in the series, and the combined stiffness and whatever the deflections are coming, we can simply calculate as per W W by K, which is nothing but as the deflection is equals to whatever the deflection in the first one plus the deflection of the another one, or we can say that the x1 is W by K1 plus W by K2. So this is the resultant the deflection is there, which is nothing but the summation of these two deflections W by K1 plus W by K2, or since the radial load is applied on both of the springs are same, so we can say that 1 by K is equals to 1 by K1 plus 1 by K2, or K1 plus K2 divided by K1 K2, or we can say the spring stiffness, if two springs of the different stiffness, if they are in the parallel region and the radial load is applied in towards the radial direction, then we can say that the resultant stiffness of these two combination of the series springs are nothing but equals to K1 K2 divided by K1 plus K2. So you see here this one, this form is the this is the basic form we can say of the series in the of the spring in the series form. But if we have the another form which is the parallel region, in which the springs are connected in the parallel and at the both end of the spring, both springs which have the two different stiffnesses, if you see the load is applied as such, you see. So if we have the two different springs, and due to the load application, if we have the same deflection, because you see both are confined by this W here, if you can see this particular diagram, both ends are exactly contacted at these two regions, and the radial load is applied exactly on the lower portion. So they are said to be connected to the parallel, because you see the parallel actions are there on both of the springs. So in this case the load is carried out by these two springs are simply shared exactly. So we can say this W is nothing but equals to the W1 in this spring and W2 in this spring. So X, the total deflection, is coming as W by K, which is the summation of these two springs. So if we are keeping those values there, what we have, the W, which is nothing but equals to W1 plus W2 as we are keeping here. So we can say by keeping those values, what we have, the resultant spring stiffness is nothing but equals to the linearly summing up of these two spring stiffness. So K is equals to K1 plus K2. So the meaning is pretty simple, that if these two springs are connected in the series, then we have the resultant stiffness is K1 K2 by K1 plus K2, and if these two springs are connected in the parallel way, then we have the spring stiffness, resultant spring stiffness is K1 plus K2. So this, you see, this part is very important, that what exactly the spring formations are and how the load is applying, and then what is the resultant stiffness is coming, and through which you see once you know the resultant stiffness, then you can calculate that actually under the application of this load how much deformation can be taken place, and then corresponding you see how much deflection can be taken place, and once you know the deflection, then you can easily get the value of the shear, this strain part, stress part, and then you can simply design the safe reason for this kind of springs. So now you see, come to the next topic, which is you see when the members are subjected by the fractional load. That means you see if we have the different kind of object, and we are saying that these object or this the main substances, if they are just under the action of various forces, just to resist those forces, if we are applying what the kind of forces, laterally or the transversely along the axis, that means you say if the force applications are there, and through which whatever the resistive forces are coming along lateral direction or the transverse direction, then these type of members are termed as the beam. That means whatever the load application is there, and if the resistive forces are coming in these two directions, we can say these objects, or we can say these bars are known as the beams. So there are various the ways are there to define these beams. So you see here we are using the three different categories to define the beam. The first definition is a beam is a laterally loaded member whose cross-sectional dimensions are small as compared to its length. So you see here, as I am saying that it is the laterally loaded, so means the whatever the in lateral direction the diameter, or you see the thickness, or whatever you see the other dimensions are, they are very small as compared to the transverse direction. That means you see the longitudinal direction. So we have a more length, and we have a small diameter, or we can say small thickness or width or whatever like that. So this is the first definition of beam, is that we have a laterally loaded member whose cross sectional area, or we can say the dimensions, are very small as compared to its length. So this is first definition of beam. Second definition of beam is a beam is simply a bar which is subjected to the forces, or we can say the couples, because you see either it is the radial loads are there, or it has under the action of the couples that lie in a plane containing a longitudinal action of bar. That means, you see, like it is always simply fixed on a particular horizontal direction, or we can say in a longitudinal axis, and whatever the actions are coming, like in terms of the point load, or we can say in terms of the different variety of loads or couples or moment or torque, then even apart from that also it is always be in the plane of longitudinal axis only, and the forces are understood to act perpendicular to the longitudinal axis of a bar. So whatever the forces are coming, they are always perpendicular in terms of compression or extension, or in terms of these kind of shearing actions are there. So if we are talking about these kind of like the specimen, then they are termed as the beam. And the third definition is a bar working under the bending is generally termed as the bending. So you see, whenever we are designing a beam, the bending action is always taken place, and we have to see carefully that actually how much bending stresses are and corresponding like the strains are there, and through which you see if we want to design safely, we have to be chosen very carefully that actually how much load application is, and under these load application what is the bending stresses and the strains are. So bending is the perfect action in the beam, and we can say that if these actions are there, it is the perfect definition of a beam. So these three definitions are there through which we can say that whatever the object is there, it is exactly termed as a beam. So now you see, once you define the cross sectional area or the cross section of any beam, then our main focus is then what is the material for beam. So the beams may be made from the several usable engineering materials based on what exactly the applications are. That means you see where you are keeping the beam, whether you are keeping a beam on your wall just you see to sustain the load, or whether you are keeping these beams in a just like you have like the swing area, or whether you are keeping the beam in the aeroplane as you shown in the below figure. So where you are keeping, so corresponding the materials are coming just to resist the bending stresses. So you see here the commonly used materials are the metals of various kinds, the wood is there, the concrete is there, and the plastics are there. Okay, so you see here, even if you can find these beams where the rails are passing and like they are simply absorbing the like the compressiveness of those things, or whether you see like on the top of floor, you see for the roof side you will find that the beam just to carry all the load. So you see there are various materials are there available for the different kinds of beam for different applications. So example of beams, just refer to the figure below. You will find that we have an aeroplane, and under the aeroplane you see this beam is all along like it is just coming. So whatever the drag and lift forces are coming, they are simply applying on these sections. So you see these beam is subjected by like as I told you, just the definition of beam, they are just along the longitudinal action. So you see this is the longitudinal axis is there, and whatever the loads are acting, they are just perpendicular to the longitudinal axis. So these load applications are like that. So if you want to design these aeroplane foils, you have to design as a beam, or if you see this particular figure, then you will find that like here we have like cross sectional beams are there, and the load application is exactly normal to this section. So probably it is also termed as a beam. So here you see we have example of beam, and material is exactly based on what application of the beam is. Now in figure 1, an electric pole has been like shown there on the top of that, subjected to the forces which is coming due to the beam due to the wind. Like the forces are coming, these drag forces are there, and they are exactly perpendicular to this pole. So as I like shown in this particular diagram, that actually when they are coming perpendicular to the plane of this particular subject, always we are termed as the pole, or any substance is as a beam. Or in figure 2, the wings of the aeroplane may also be regarded as a beam, because the whatever the aerodynamic actions are coming, the drag and with this lift forces are coming, they are exactly perpendicular to the longitudinal axis, or we can say whatever these responsibilities are there of this particular action, aerodynamic action, is just to provide the lateral loading on these particular members of an aerofoil. So we can say that either these aerofoil section of an aeroplane, or these like the poles, or any kind of this cross section, if they are under the action of these like the lateral with this perpendicular loading in the lateral directions, when it is just lying in a plane of a longitudinal axis, these are termed as a beam. Okay, so this is the basic definition of the beam is, and the material was there actually which you can chosen. It can be chosen at any way just based on what applications are. So now you see we have the geometric forms of a beam. So the area of the cross section of a beam may be taken in several ways. So like, and it depends on what area you have chosen, corresponding applications are there. So like you see, we can either choose the rectangular area cross section, that you see you have a beam which has the cross section of the rectangle. So you see rectangle cross section, always it will give you the clear feeling about that actually how this central axis is to be there. That means the central axis which is passing from both of the way, it is just uniform. So if you want to design the just like any of the bending stresses distribution, or you see if you want to see that actually how the shearing is taken place, you can simply see that neutral axis is well defined. You can simply define this neutral axis, and you can like define the reason of these bending stresses are whenever we have a rectangular cross section, and a corresponding you see you need to choose on the effective the dimensions to calculate that effective area. So this is one like the cross section is there of a beam, that is a rectangle, or we can like we can be choose also the T section, or you just what we need to do here, we simply removing this material, so that like once you remove the material you have less inertia because the mass is now removed, so less inertias are there. So if you are designing a beam which like in which the weight is the main criteria, the T section or another the I section always gives you like the minimum weight. But as compared to even the T section and I section is more like the symmetrical part, because you see here on this particular top and on this top we have the balanced way, and in between you see there is a connection. But as compared to the T section, you see we don't have this particular section. So in some of the application it gives you a imbalanced cross section. So sometimes you see whatever the bending stresses are forming under the action of these loads, they are not uniformly distributed. So probably you see for the safe design of any kind of beam where the load actions are there, always I section is very popular, and whatever the bending stresses are there, they are always coming in the very symmetrical way. So this I section, because you see here this much weight is removed, this much weight is removed as compared to this section, so it has a less like the mass moment of inertia, or we can say it has a less weight. So like whenever this kind of motions or whenever this kind of analysis is there, this I section is very popular. Then you see the another cross sectional areas are the triangular cross sectional area. So you see like whatever the beams are there, they have a flat, and these cones are there at these two corners, and it is to be connected. So we have this kind of beam, or we have a circular cross section, like if we have a circular prismatic bars are there, and if it is under the action of the perpendicular load or any twisting is there, so probably we can use this kind of circular bar also. Or if we have a channel which is you see like just this channel is there, and there is a gap, means there is a groove is there all across that particular this length of the beam. So whatever the cross sectional area is there, corresponding dimensions are coming, and corresponding like the affected area will be considered under the action of these forces, and these forces are always perpendicular to these longitudinal axis, or the couples are coming, twisting torques are coming. So we have to be very careful that actually what exactly the effective areas are there, or the important thing in any of the beam is what is the cross sectional area, because you see like when we are talking about any force or any stresses, the affected area is firstly concerned, because when we are talking about the uniform distribution of the stress, that in which area it is to be distributed, and whether you see like any kind of stress concentrations are there or not, we have to check it out those things. So that's what you see like even in this also, when the bending stresses are forming all along this prismatic bar or this kind of beams, always we have to be very careful that which area is to be chosen first for the safe design, and how like these area are to be like considerable under the action of these forces. So now you see issues regarding with the beams are like whenever a designer would be interested to know the answer of the following issues while dealing with the beam or the practical engineering applications, because as I told you it has a lots and lots of application of a beam. So you see first of all, at what load will it fail. So first of all you see like as we know that it is like in the longitudinal axis and the perpendicular loads are coming, so how much load it can bear. And you see how much, up to what extent you can go that first it will go to the plastic deformation under the action of bending, and then it will rupture like, or the fracture will taken place. So first of all, the first key issue is there, that how much the of this particular beam the load carrying capacity is. And the second question is again important, is how much deflection occur under the application of this load, because you see when you are applying the load, there is a different kind of like the distortion, or we can say the deflections are coming in this kind of beam. beams. So again you see we would like to see that at, which portion is under the action of tensile or which portion is under the action of compressiveness is. So based on that you see we would like to design those beams are. So based on that again we would like to classify these beams, because now you know the beam, you know the material of beam, you know that what the loads are this load can be applied and what the cross sectional areas are there. So now based on these things you see beams are classifying on the basis of their geometry, as I told you, the cross section as just in previous we discussed, and the manner in which they are supported. So there are two main issues: one, what is the geometry of this beam is, and second, under which what is the manner of the load application is, or how they are supported, whether they are supported at the both ends or whether one end is supported, or whether it is supported on the roller end, or rigidly support is there of both ends. So there are a variety of these kind of supports are available, and based on that actually we can simply classify those beams. So first classification is basis on the geometry, normally includes the features such that the shape of the cross section and whether you see the beam is straight or the curved. So generally we are talking about what is the cross section of the beam is generally and we already discussed the various cross sectional part of the beam, just like whether it is a square cross section or the round cross section, or is a I section beam, T section beam, or whatever like that you see so first is this, what the cross section is there, means what the cross sectional shape of that particular beam is, and the key feature is that whether we have a curved beam like that or whether we have a straight beam. So if we have a straight beam, then all you see the design criteria is different. If we have a curved beam, then all design criteria is different, because you see whatever the bending stresses are coming in the shape of straight beam or the curved beam is altogether different. So this is the first classification, and the second classification says that the beams are classified into the several groups depending primarily on the kind of support used, as we discussed that actually what kind of supports are there at the two extreme corners. But it must be clearly understood that why do we need the support, means what application is there, why the supports are there, whether you see both ends are supported, whether one end is supported, what exactly the application is there, and what kind of loads are coming on that beam. So we have to understand first of all understand this kind of phenomena, then only we can say that yeah, this beam is of this nature. The supporters are required to provide contaminant, or we can say the movement of the beam, or simply supported the kind of supports resist the movement either in the particular direction or the rotational direction or even the both. So this is the real feature, that actually why we need the supporters, just to withstand those things, or just to provide these kind of resistances in terms of the movements, or in terms of in a particular direction the kind of movement, or it's a kind of rotational part. So what exactly these supporters are doing there. So based on, once you know that this kind of the applications are there and the corresponding changes are coming due to these supporters, we are simply classifying these beams are. And then as a consequence of these reactions, once when you have the kind of the supporters, always the reactions are forming due to these supporters. So what the kind of reactions are coming into the picture, whereas to resist the rotational movement of the moment coming, or we can say the bending moment which is coming into the picture, that is the key issue, that how these reactions are coming, because when you are designing a beam under the action of these bending forces, always one has to be very careful that actually how this bending action is taken place and what the reactions are coming, and one has to consider the reaction very carefully, and on that basis these particular supports, the beam may be classified as cantilever beam. First of all, cantilever beam is nothing but, you see here, if we have a the beam which is the same definition as we defined, that it is the whatever the lateral parts are there, the dimensions are there, they are very small as compared to its length. So we have a beam, and if one end of beam is rigidly supported, so as the one is a beam which is supported on a fixed support is termed as a cantilever beam. Now let us understand the meaning of a fixed support. Such a support is obtained by building a beam into bricks wall, or we can say casting into the concrete or welding end of the beam. That means, you see, if I am saying that the cantilever beam, that means one end is rigidly supported at one part. That means, you see, either this beam is going into the wall, or this beam is casting into the concrete wall, or we can say we are simply welded. We have this wall and we have this beam, so it is welded at this particular section. So this end is free and this end is rigidly supported. Such a support provides both translational as well as the rotational constraint to the beam. That means, you see, if you have this particular rigid support at this particular corner, then you cannot get any kind of translational motion or the rotational motion. So it provides the rigid resistance against these two kinds of motion. So it is the real constraints for translational as well as the rotational motion. Therefore the reaction as well as the moments appear are just, you see, we can show that this is the kind of cantilever. We have a rigid support, this beam is rigidly fixed inside that. So you see, it will always try to resist whatever the kinds of, like the translational as well as the rotational forces are coming on that. So you can see here, if you apply any kind of load, it will sustain that kind of part, you see, either this moment or this kind of reactions in both of the way, this in a horizontal way or this vertical direction. So this is a basic form of the cantilever beam. So whatever the load applications are there on this particular free corner of these, you see, on any of along this particular length, any of the part, this can be easily, sustained by this kind of rigid support, and this form of the beam is known as the cantilever beam. Second, you see, the based on what kind of supports are there, second category comes as the simply supported beam. The beams are said to be simply supported if their support creates only, the translational constraints. That means, you see, just you see, whatever the translation motion is there, if we are keeping the support such that actually they are just provide the resistance against, that kind of motion, we are saying that we have the simply supported beam. So you can see here, we have, like in this diagram, we have a straight prismatic bar, or we can see the beam is there, and we have a pin joint. So the pin joint is simply, given this kind of motion here. So whenever and a kind of load application is there, the reactions are coming in terms of this vertical as well as the horizontal direction. So you can see here that how we can represent this kind of forces and this particular pin joint. So if we have this beam, and if these pin joints are there, this particular, so the reactions are forming under the action of any load in this vertical direction is known as the Ry reaction, and the horizontal direction as the Rx reaction. Sometimes the translational movement may also be allowed in one direction with the help of the rollers, and that can also be presented in the next, like the figure that you see, we have the roller, and you see we can allow, movement of this particular beam in the only x direction. So once you see we have the roller, so this is the roller, you see, or we can say this is a kind of roller is there. So in that only the vertical forces are dominating in that, or we can say the directions are coming. So we need to show this kind of thing. So we have a beam, we have a roller, and this reactions is there on just to provide the resistance. So that's why you see the Ry is there in the vertical direction, or we can simply shown in the different picture that we have, and which is the general representation of this beam under the roller. So you see here these rollers always allow this beam to move in the x direction, either of both side, either this side or that side, according to what load applications are there. Or we can say here a roller can resist the force that acts perpendicular to the plane of CD. So you see here, it is not that a straight one is there, even if it is at a twisting angle, these like the pin joints are there, these pin joints can be acted as a roller at this particular way, and you see the reactions are there which are coming along this particular line of action. So here you see which is exactly perpendicular to this particular plane CD. So these reactions will be going along with along with this line particular. So you need to resolve these reaction forces in just by taking theta, because this is the straight line, the theta. So r cos theta and r sin theta. So how these theta will come into the picture, r cos theta or r sin theta, and how they will act as reactive forces one has to consider. So this is, you see, the simply supported beam was there. So now you have the two main forms of the cantilever beam, the beams based on what kind of supports are there, and that's why you see we are classifying accordingly. One, we have a cantilever beam in which one end is rigidly supported, nothing has to be happen in terms of translation or rotation, and one end is absolutely free. So either we can apply any kind of moment, point load, or whatever the kind of things are there, the concentrated load like that. And other is, you see, we have a simply supported beam in which the reactions are there. If we have the pin joints at both the end, so this will allow this particular beam into in the kind of movement under the application of load, either it is going in the bending side or the shearing part. So we can simply take the reaction forces in x as well as the y direction, these two mutually perpendicular reactive forces. And the another form of the simply supported beam is that if you have the rollers on that, then definitely you see the reactive forces are coming in the perpendicular direction, irrespective of whether this pin joint is the straight one on the roller or this pin joint is the tilting part. So these two forms of the beams which we discussed here. Now you see we would like to discuss the statically determined, or we can say statically indeterminate beams are. The beam can also be categorized as the statically, means under the action of the static forces determined, or else it can be referred to a statically indeterminate form. If all the external forces or the moment acting on it can be determined from the equilibrium conditions all along that. That means you see, like if we are, and this is the biggest assumption in all the beam theories, that under the application of all the loads and the couples or the twist, you see this beam is a well equilibrium manner. That means you see it is well balanced. Then when you apply the load, when you apply the torque, it is like going under the action of bending stresses. So how these bending stresses are being set up along this particular beam, and you see if you are saying that they are well balanced, that means you see the counterbalances are there of these stresses, and accordingly this balance theory is there, and that's why you see we are saying that these beams are nothing but the statically indeterminate beams. And then it would be referred as an statically determined beams, whereas in statically indeterminate beams one has to consider the deformation or deflection to solve the problem. And that's what you see we are categorizing two main ways. One, if we are talking about the statically indeterminate form, then only our main focus is on the stress and strain, and then corresponding you see all like that how these bending stresses are forming and what is the bending moment is there, and how we can calculate all blah blah things based on the different cross section. But if you are talking about that if our beam is statically indeterminate form, that then you see our main focus is how the deflection is there, and then you see the deflection theory is there. So it is altogether a different chapter and altogether a different concept is there. So you see here we are categorizing the two main ways. One is the statically determinate beam, or second is the statically indeterminate beam is. So with the statically determinate or statically indeterminate beams, now like we would like to see that whether whether it is under the deformation or under the deflections are there. Now we would like to categorize those beams based on what type of load actings are, because you see as in previously we have discussed that actually whether it is like the cantilever or simply supported beams are. So now a beam which is normally horizontal, whereas the external load which are applying or acting on these beams is generally in the vertical direction, and we that's what the definition of the beam is, that the beam is always lying in a longitudinal axis, and these loads are just perpendicular or normal to this particular axis are there. So always this is a pretty common nature of the loads are there, that they are always perpendicular to the longitudinal axis is there. And in order to study the behavior of the beam under these flexural loads, we have to be very careful choosing of this kind of loads are there, that they are mutually perpendicular. It means this axis is this, and they have to be acted on the perpendicular axis or the normal to this particular beam. And it becomes pertinent that one must be familiar with the various types of loads, that what types of loads are acting on that particular beams, as well as their physical manifestation, that actually how they are appearing, and due to that actually what kind of the deformation or we can say the stresses are being forming, the bending stresses or the shearing stresses due to that particular thing. And since we know that the bending stresses is nothing but the combination of the tensile as well as the compressive stresses. So you see here again we would like to classify this kind of beams on the basis of the types of load. The first type is the concentrated load, means you see it is a kind of load which is considered to be act as a point. Like you see we have like the 10 Newton is there, or hanger is to be or we are simply keeping some the point loads on a particular just a section where all the load is to be concentrated. So this kind of load is known as the point load, or we can say the concentrated load. By this we mean that the length of beam over which the force acts is so small in comparison to the total length, means actually this is simply acted as a small portion as compared to the bigger length of that. One can model those force as applied as a point in two-dimensional view of a beam. So as I told you that actually if we have let us say this 2 meter this length of beam is there, and this the point this load is just we are simply keeping the load, and this effective area under this load is let us say just 10 centimeter. So in comparison to the 1 meter or 2 meter load, 10 centimeter or even the 5 centimeter is nowhere comparable. So we can be treated this concentrated load as a point load, and generally you see we are saying that the point load is acted vertically downward or upward like that, and the constant magnitude is there. So here in this case, the force or load may be made to act on a beam by either hanger or through by various means, as I told you, like just keeping the effective load there, or by just putting exactly that actually what the kind of like the distribution is there, the load just concentrated on that particular point is there. So we can see even like here that we have this the simply supported beam. So here you see these two pin joints are there, and if you see this particular figure, then you find that this beam is like spread all across this particular these two this fixed supported beam, and at these 2 points you just see these 2 points here. What we are doing here, we are simply keep the hanger, and in the hanger we are simply keeping the load. So the effective area under this load is this much. So as compared to this entire length of beam, if you compare this particular area, you will find that it is a very tiny part as compared to this, or either this one or even to W2. You see, you will find that this effective area under which these loads are applying is very, very small. So we can be treat these loads as a point load, and generally we are saying that the concentrated loads are the point loads, and simply we can justify those things by giving the indication, just point indication towards the downward direction here as this point load W1 and here the point load W2 for this simply supported beam. Then you see like the second kind of loads are the distributed loads. The distributed load is a kind of load which is made to spread over a entire span of a beam or over a particular portion of a beam in a specific manner. That means you see here in the previous part we have seen that only the concentrations was there. That means you see only the effective area was very, very small, but here you see now intensely we just want to spread this load over the across the length of the beam, so that that particular area is to be affected by that much load. So you see here if you want to describe those things, here the figure is on your screen. We have a kind of simply supported beam, and you see here what we are doing here, we are simply put the distributed load. So this you see this load is not concentrated. This entire load which has a magnitude, the rate of loading is Q of x. Q of x is nothing but you see this load Q is distributed for this length x. So this Q is a function of x. So it is you see uniformly distributed in this particular area. So generally you see we are treating this load as the uniform, this is a distributed load, and this is always be given in terms of Q of x, or we can say the rate of loading, because the Newton per meter or millimeter, that how much you see in how much millimeter or a meter or centimeter this 10 or 20 or this load is spreading out. So you see we will find that this is the effective area under which on which these loads are acting, and we are treating it as a distributed load. So in above figure, the rate of loading Q is a function of x. As usual you see the distributed load is always a function of x, that is the span of a beam, and hence you see it is a non-uniformly distributed load, because you see we if the impact of this load here is more, here it is less, here it is less. So we can say that this is a non-uniformly distributed load is. But if we are taking the load, rate of loading this Q, our length of a beam may be uniform if you are just taking the entire span of a beam. That means you see in this figure, if you are taking the simply supported beam, and the total this beam, this area of the beam is affected by this Q load. So this Q is now just applying on the entire span of the beam. Either we can represent by this point loads on those total you see, or we can say this load is spreading on all across the length of the beam. So we can say this kind of load where the load is totally affected the whole area of the beam this load is known as the uniformly distributed load UDL, and the UDL may be like represented here by the both way, either the point load all across this particular like the length, the points are there, or we can say these spiral parts are there through which we can say that the Q of x is there, and the Q of x is always it's a rate of loading of either the distributed load, or we can say the uniformly distributed load, and always it is coming as Q Newton per meter or kilonewton per meter or Newton per millimeter, whatever you see the units are there. That means you see what is the affected length is there, or which this load is coming, always the unit is like that, actually Newton per millimeter or meter is. So you see here, this is the another kind of loading is there, in which the entire span or a specific region is affected by the load is. It is not the concentrated load where only the small area or the segment is affected. So now you see here, this was the second kind of load. Now sometimes you see the load acting on the beams may be uniformly varying, as it in case of the dams, or we can say the inclined wall is there on a vessel containing the liquid. So you see, if you just want to analyze like the dams, where you see like the this water is just having a varying height, that means you see like at the very close section the heavily loaded part is there, and at some end you see like the water is just touching on the surface of that. So if this kind of loading is there, we are always saying that this is the triangular loading, or we are generally like taking if we have a vessel in which the liquid is flowing, and we will find that always liquid is at some height, you see if it is in the inclined part, at some portion it is heavily like the hydraulic pressures are there, rho g h is there, and at some part you see it is just touching to the road. So this kind of loading is known as the uniformly varying load, or we can say the triangular load is there, which has you see the tendency at one the simply supported beam, always the maximum load is there, and it is simply varying. So it is not uniformly varying, it is varying in a uniformly this tapered section way. So we can say that this kind of UDL like, or we can say like this kind of load is known as the triangular loading. So the UDL can be easily like realized by making idealization of the like warehouse load, or where you see we can say that the bags of grains are simply placed all across the beam. That means whatever the grains are there within that particular beam, they are absolutely placed within their own places. So whatever the distortion or the deflections are there, it has to be uniform, and whatever the bending actions are there, they have to be uniform. But in this case where you see this kind of loading is there, we have to be chosen that actually where is this concentrated part is there. That means you see where the center of mass is there, through which these bending loads this bending can be occur, and then corresponding you see we need to check the effective area under which these bending loads are. Because you see here, if we are considering this portion and if you are considering this portion, one has to be taken care that actually what is the effective area is there, and how much load is to be applying on these areas, since this load is varying with the length. So you see we need to check that actually where is the center of masses of this particular load is. So that's what you see like this is the third type of load is, in which the triangular loading is there, and it has general application. Now you see we are going for the next one, that is the concentrated moment is. So the beam may be subjected to a concentrated moment essentially at a point, because you see it is a moment is there, and the concentrated moment will just tend to move this beam in a particular direction. So you see the complementary moment will come just to balance this moment. One of the possible arrangement for applying moment is just you see like we are going to see in that way. But prior to that, you see if we want to balance those things, always what we are doing here, we are keeping those like the kind of beam in that way in such a way that these two reactions, whatever the reactions are coming, they will balance like they will balance whatever the unbalances are coming due to the applied load. So this is you see the kind of a uniformly distributed load, and if we have the triangular load, we will just try to counterbalance the remaining load so that the balancing will be formed, and we can say that it is the statically determinate beam is. So now you see like in the concentrated beam we can see that what we have a simply like this kind of a beam is there. At one end you see like the simply supported beam. So when we apply the moment at these two ends, like it will just try to tend in a such a direction that actually like it will just moving this beam into a clockwise direction, and then this beam will try to tend, or we can say the like this consequences are coming in such a way that this has reactive forces in this opposite direction, or we can say the clockwise direction. So what will happen in that case? This beam has a tendency to move in this direction. So we need to design in such a way that whatever the shearing action is here, or shearing action is taken place, or whatever the couples are forming, at what point these couples are forming. Because you see, if you see this particular point, just concentrate on this particular figure, you will find that you have like this couple, and the origin of the couple is this. So whatever the couple is coming, it is coming due to this like the reactions. So you see here, this due to these forces, it is tending to move in this anti-clockwise direction. So what will happen? This portion will be under the action of the tension, and this portion is under the action of the this compression, means it will just tend to move in the upward direction. So you see, this due to this couple, this bending will take place. That means it is going in this direction, and we need, you see, the counterbalance of this kind of couples to balance that. Or if you want to compute those things, what we have like if you just replace these pulleys by these forces, we have, you see, like the force direction in this direction and another force in this direction. And you see, when you have like this force, and when you have this like the distance, then you can simply compute the moment, which is nothing but equals to force into distance. So this moment will be acted at this point. So this is, you see, the exact, you see, the axis of the action through which this moment will be applied, and this moment will be like going in this direction. So the whatever the resistances are coming, which will be coming in the anti directions. So you see here in this chapter, what we defined like the main, if a subject is under the flexural loading, then how we can define those like the structure. And those structure, we are simply defining that actually it is known as a beam, irrespective whether it is a straight beam or curved beam. Generally, you see, in this chapter only we discussed about the straight beam only, where we have the length is very large, but whatever the lateral dimension is, irrespective of the thickness or diameter, is very small. And then we discussed that actually this particular kind of beam having a various kinds of cross section depends on what kind of application is. So you see, if we are talking about like that where the weight criteria is very much, and you see we just want to reduce the weight with the same kind of bearing bending actions, we are always preferring the I section. And we like in the next lectures or so, we are going to derive that actually why this the section modulus or this bending stresses are really uniformly distributed in the I section, and why I section is fruitful. So but you see, we had a variety of the sections, as either rectangular section, circular section, triangular section, I section, T section. So you see all like the channel section. So all these sections have their own unique features, and corresponding to the what kind of applications are, we are choosing these sections. So that's what you see, we discussed about this like this straight beams and this kind of sections. And then we discussed an important issue, that how we classify the beam. We can simply classify based on how they are mounting, or what kind of supports are there in that. If we are saying that one end is rigidly fixed and one end is free, this is a cantilever. So in that, you see, whatever the constrained motions are there in the rotational as well as the translational direction, it is to be rigidly fixed by one end. So there is, it won't allow this beam to move or translate any kind of motion in one direction. So but one end is free, where we can apply any kind of like the loading, and we can check that actually what exactly the bending moment or the bending stresses are forming within that kind of beams. And the second beam which we classified in that category is the simply supported beam was. And this simply supported beam, you see, like whenever the kind of loading is there, there always two reactions are always forming in the horizontal as well as the vertical direction. So Rx and Ry is there, and in that also there was one more category was there, that if you allowing this motion in the longitudinal direction, or like the transverse direction, then you see only one reaction will be formed. That means whatever the resistances are coming from these supports are only in one direction, that is the Ry. And then you see, like we checked it out, that actually if we have these pin joints in at a particular angle, then how these reactions are taken place. So that's what we discussed about these, either the cantilever beam or simply supported beam. And then you see, we discussed that what kind of loadings are there through which we can even classify the beams. So you see here the main two types of loading which we discussed. One, the loading is the concentrated type. So you see here, if we are keeping the hanger or if we are keeping direct loads on a particular area, so under these like the effective area under these loads are very tiny as compared to the entire length of the beam. So that's why you see the concentrated loads are sometimes termed as the point load, and generally you see we are simply notating these kind of load by a simple arrow towards either the vertical downward or vertical upward directions. So this was, you see, the concentrated, or we can say the point load was there. And the second category which we discussed in the load condition is the distributed load. So distributed load is always distributed on the entire length of the beam, either for a short span or for full span of the beam. So if it is a short span of beam, then it is the non-uniform distribution of load, because the impact of the load over this total length of the beam is non-uniform, and whatever the stresses are forming, they are always in the non-uniform way. But if you see this this load is spreading all across the length of the beam, then we are saying that it is the uniformly distributed load across the span of the beam, the full length of the beam. Then you see we are again denoting by UDL, or it is just showing by the weaving, and this kind of load is always not coming in the Newton form, it is always coming in the rate of loading. So they have, you see, either the kilonewton per meter or kilonewton per millimeter. And the third kind of loading is, if we have this kind of the figure which is showing on your screen, if we have the kind of twisting or the moment is there, then again you see the two different actions have to taken place at two extreme ends. Like one is at this tensile and one is the compressive one. And how to design those things, you see, again we need to check it out, that what is the point of application, or we can say what is the origin of this kind of moments are. Once you know the origin, then you can simply found the you can easily form these the moment by taking whatever the load into the distances, and then you see from from this end, the left end or the right end, how these bending stresses are forming within this this beam can be easily evaluated, and then corresponding designs to be taken care. So in this chapter we discussed all those issues about the basic issues about a beam. Now you see here we would like to see that if a beam is under the concentrated load only, and if it is the cantilever beam or a simply supported beam, then you see how these the bending moment will take place, and how we would like to calculate those moments with the kind of reactions are there, and we would like to draw the bending moment diagram. And also you see, when there is a bending action is there, the when there is a bending formations are there, always shearing actions are forming, because you see that these two even if you are talking about a simply supported beam or a cantilever beam, the kind of reactions are coming from the bottom and the top, or from the top action you see the load action is there. So shearing is there at these two corners. So how you see the shear forces are coming, and due to that you see how the shear force diagram we can draw. So these two are the real good diagrams to see the feasibility of the load, and what the we can say that how these loads are forming, and due to this load how these this beam is behaving. That kind of the phenomena which we would like to see in our next chapter. Thank you.
Thank you.